Thank you, Chair. I guess I should say honorable guests or distinguished guests, ladies and gentlemen, good afternoon. Thanks for the opportunity. If you've just listened to my CV, you might find this interesting that I'm going to talk about unlocking the potential of shale gas through technology, and you might think that I'm just going to talk about one angle of this. I'm going to try and cover both sides of the spectrum, and let's see if we can get this thing to work, and really start the conversation maybe with what I can call at best Petroleum 101. I guess many of the people in the audience, just like myself, are not necessarily working with this part of the industry every day. I'm really going to try and approach this quite generically, look at what's been done elsewhere in the world, and then at some stage I'm going to try and build a bridge between that and the Karoo shale prospect. And then towards the end I'll start to get into the area that is really my forte, and that is the technologies when it comes to the downstream application. Okay, so I guess, and this is a slide that I got from one of our petroleum engineers. If you start this conversation, you need to some basic definition, and the first one is, so what is a petroleum system? And I guess this is a definition out of a petroleum handbook. It says a petroleum system encompasses a pot of active source rock and all the genetically related oil and gas accumulations. It sounds very complex, and the elements are source rock, you have the reservoir rock, there is the seal rock and the overburden rock. So this is the details in terms of what is below the surface, the stuff that we don't see. So in a conventional system, these elements are all separate. You would have the source rock at the bottom, you could have reservoir rock, a seal rock, overburden rock, and if you're lucky, you might even have a cap of gas somewhere in the system. So that's a classical conventional petroleum resource that I think we've been known for a long, long time. In an unconventional system, however, all of the above is essentially trapped in one layer. We have all of those elements basically trapped, and as it says, it says that it's essentially a source rock that's got favorable mechanical properties to produce directly. Okay. So if you look at a typical well, as one would have when it comes to the production of a shale resource or an unconventional oil or gas, the typical element would of course be the vertical section of the well in combination with the horizontal section. Typical numbers are the depth, typically in the range of somewhere between 5,000 and 10,000 feet below the surface. The horizontal wells could typically be up to about 3,000 meters. And then of course you have the casing, and in the areas close to the surface, there's the additional protection in terms of the additional casing plus some of the cement that is being added to protect the groundwater surfaces. So the essence here is, how do I get this rock to talk to the top side? And that is what I guess fracking is all about. You need the fractures in the rock, and you need a mechanism to provide continuity between the rock and the wellheads, so that you have an active system that is producing. And this is what I think what shale extraction or unconventional oil extraction is all about. Unfortunately, it doesn't stop there. It becomes, as somebody says, the plot thickens. In a conventional system, the system is typically constrained by geological boundaries, which means that the field has a definitive size, it's bound, it's constrained by that, it's normally big, and that means that you typically only have to do 1 or 2 wells to produce and basically capture the value from the resource. In an unconventional system, it's not the same. Here you have with a system where you have multiple wells across the resource. They're all producing. Unfortunately, they're not all producing at the same rate. Some of them are producing more than others. And if you're very lucky, you're going to have areas where you have a number of wells that actually produce at relative high rates. In other words, the so-called sweet spots. And I think the challenge here is to have enough of a mathematical average in terms of the volumes that you produce from the resource to support the economic thresholds required for commercial production. So I guess it's obviously clear that the approach to the development of an unconventional resource is quite different than the approach that we've historically seen in a conventional resource. If one would endeavor to develop an unconventional resource, I think the first thing to realize that it is going to take you time. In order to succeed, you need to take a phased approach, and you need to make sure that you generate enough understanding through the various phases to ultimately inform that very big commercial big decision whether or not to implement the commercial side or go commercial production. Typically in phase one, the focus is really on trying to identify the presence of, I guess, the unconventional resource. In other words, the presence of gas or oil. And typically, this involves a geological assessment. And as the slide says, it is about to determine whether there's the potential of hydrocarbons. That's effectively all what phase one is all about. Phase two is when you start to actually explore a little bit more directly in terms of what is below the surface, and this is done through vertical drilling. And the objective is to obtain core samples, which is really then used to look at the reservoir properties, to try and get an estimation of the resource potential, and also to try and get a feel for where the limits in terms of the resource field is. In stage 3, you also then combine the vertical and the horizontal drilling, and for the first time you start to experiment with actual fracking technologies. This is the time where you start to produce, you start to test the flow in the system, you try and optimize on the let's call it the fracking recipe, and you also try to determine the engineering properties required to do the engineering of a commercial construct. The last stage before commercial is actually pilot production, where you basically repeat what you've done in stage 3, just at significant more advanced conditions, and where the focus is really, how do we optimize the resource to support the commercial decision that is to follow? How do we make sure that we have enough information in terms of what we can expect in the mix to convince management that the statistical average of what we're going to get will support the economics over the life of the project? And if you're lucky, you can do that, and then you go into commercial production for as long as the resource is there, and ultimately you need to come back and you need to reclaim the land and basically protect the environment. So I think the key thing here is it's not going to happen overnight. It's a lot of effort required. It requires a staged approach, and progressively, I guess, the level of information and the quality of information improves to that point where you can make the commercial decision. And I think this is typically what you need to be ready for. You need to expect heterogeneity, and you need to plan, and I guess it's a bit of an American term, for the long game. I think the slide shows, and this is from, I guess, the Southwestern University or Southwestern Energy. It shows basically the production mapping of a number of wells in the first year of production, and you can see the statistical difference and in terms of production between the various wells. I think what you need to recognize here, and what I'm trying to say with this slide, is that you're going to end up with wells that produce both high volumes, but equally with a number of wells that might be producing low volumes. You are going to rely on the statistical average. You're going to rely on that statistical average to convince your management that there's a viable economic proposition here. And I think it is important that you make sure that you understand the resource sufficiently so that you can decrease the probability or the risk, as it said here, of completing some of these low volume producing wells, because they don't really add to the economics, and as a matter of fact, they pull the statistical number down, which is not what you want in the commercial construct. I like this slide because I think the notion of being on the treadmill is a good example of what it is like when you go into commercial production. And what what this is trying to highlight is, I think, the uniqueness of every well. And I think the important factor here is the fact that every well has a production curve. And the very important factor is that initial very steep decline in production that you get typically in the first year of production. And as the slide indicates here, it could be as high as 60 or 80% of in the first year in terms of the production profile. So again, you need a number of wells to actually produce the production. But it also means that you need to be on that treadmill of drilling and completing all the time so that you can almost get ahead of the curve. You need to be at the point where you can account for the production decline of what you have in the ground and actually add more capacity to actually support the ramp up that you desire in the field. And I think the last point there is this requires that you need to have access to sufficient land so that you can actually do that and have a meaningful drilling program. Okay, from an operational perspective, what is important then is you need to optimize, you look for economies of scale, and you need to have this land base where you can do this rolling production planning. And you can enhance that by working with others, by looking for service sector alliances to support what is required on a large scale. And in a number of cases, the operators also look at owning some of the critical resources, owning the land, owning water, and I guess on a number of other areas also owning the infrastructure, because whatever you produce, in particular when you have a gas-oil mixture, you need to separate it and you need to get it to market. Okay, so what are the key learnings here? Let me try and touch on this. I think it says, and this is from North America, shale gas exploration and development is capital intensive and it requires a well-developed exploration strategy. I think a staged approach is required. Understanding the reservoir properties is critical if you want to achieve commercial success. You need to be in a position to design for repeatability to make sure that you can ultimately optimize the whole production phase. And I guess the last one there is, this heterogeneous nature of the resource, and you need to understand that if you really want to understand the impact of that on producibility. So let's just take a pause here and start to look at the role of technologies. If we look at technologies, I think let's look at technologies from the perspective of finding the resource, assessing the resource, and then also producing the resource. When it comes to finding the resource, the most important technology that you need is humans. And you need a specific integrated approach as far as the disciplines of geoscience, engineering, and the environmental disciplines are concerned. Of course, you need to understand what is below, so the seismic program, be that 2D or 3D, is a critical part of the toolkit. And it says there a typical 3D survey can cover 500 square kilometers, so you need to be ready for that. You need to have the hardware to process the data. You need to have the software to optimize and deal with the volume of what's coming your way when you start to do this. And ultimately, you need to be in a position to drill these exploratory wells so that you can actually increase the database of what it is that you require. When it comes to production, it is again about the drilling technology, it's about the completion technology, it's about the hydraulic fracking, understanding, I guess, the options there. Dealing with water. The slide indicates as much as 36,000 cubic meters per well and 1,500 tons of sand per well. So start to think about scale and the management associated with that. And then in terms of the permanent side, again, it's the top sides, it's the casing, it's the tubing. It's really the surface facilities, the infrastructure required. So not necessarily high-tech, but I guess fairly complex and huge volumes to pull together in a single outcome. So moving and changing some gears and starting to build a bridge between the Karoo, I think a couple of points to make here. The first point here is the potential is undeniable. But I guess by now, given how long this potential has been on the table, potential not developed will not generate any value. So the question, I guess, in South Africa is whether this will remain potential or whether any value will be derived from it. I think the other one is maybe a bit of a reality check on ourselves, and this slide is trying to give a pictorial comparison, more or less to scale in terms of the Karoo in comparison by what has been done in the United States. And I think this in itself gives you a picture of some of the challenges associated with this. What this is also not showing you is the interconnectedness and the pipeline network that you have in the United States, which makes it a lot easier to start to produce and develop a shale facility like this. Okay, so what are the risks and the challenges? Lack of data. I think the existing well data is actually quite sparse, which means that more work is required to increase the database. There is a potential that the Karoo Basin might be over-mature, that it's possibly depleted by volcanic action. Just means that more data is required to understand this. There's the lack of existing infrastructure. I think I've talked about infrastructure and the role that this would play in the development of a shale play. Water. I think water is a very important commodity. And I don't think we have to go into the details in the Karoo. I guess the plus side to this is in the US, they've actually demonstrated that water usage can be optimized. And I think the last thing is, as a shale play or a play like this develops, and as it matures, I think you start to get economies of scale. There's the potential to impact this through implication or the application of new technology. I refer to CO2 fracking, foam fracking. Those are some of the emerging trends out there that could potentially impact, the suitability of or the feasibility of what we're doing here. And last but not least, again, water. And in Canada, water has become a commodity that is now tradable between companies. So it's not just a resource that somebody has to find, it's a tradable commodity. All right. A couple of slides just to talk about the downstream application. What this slide is trying to show is that once you have the gas, there's actually a lot that you can do with it. I've tried to paint a picture here in terms of those possibilities that are mature, which are immediate takers of the gas. In other words, there's relatively low risk in that. The second would be those possibilities where there is still commercial uncertainty, economic uncertainty. And the third element would be those possibilities where the technologies are still emerging, so you also sit with technical or technology uncertainty. I guess this is probably or possibly stating the obvious if you look at the mature takers of the gas. I mean, the first one would be, why not PetroSA? The facility is there. We all understand the predicament of PetroSA running out of natural gas as a feedstock, so it almost seems like the obvious choice. There's also a high volume demand, so the ability to ramp up quickly from a market perspective is there. I guess the alternative is to build a pipeline and hook it up to the Sasol network, which will then potentially enable Sasol to use this gas from a facility like that to augment the feed to existing facilities. In the process, of course, you will unlock pipeline gas opportunities. And I think the important benefit of these opportunities is the fact that you have takers of gas at volume that can do so immediately. Often a challenge when you develop a gas resource. Another one that I think is probably the obvious one is gas to power. If you look at gas to power in terms of its CO2 footprint, it is still a lot better than some of the conventional ways that we apply in this country. I think there's also a good fit between gas to power and the whole drive towards renewables in dealing with the cycles in that production profile. So there's another obvious one to think about. If we now look and change gears a little bit in terms of those areas where maybe there might be some economic uncertainty, in other words, you have to build the facility. The first step would be to convert the methane into syngas. Once you've got the syngas, basically a combination of hydrogen and carbon monoxide, there's a lot that you can do. You can go the Fischer-Tropsch route. In other words, what Sasol have done. There's a couple of things that you can do there depending on the catalyst system that you want to use and depending on the product mix that you are chasing. But you can also go the methanol MTO route, where effectively you would be creating either an ethylene, basically it's a combination of an ethylene and a propylene platform, which could be the platform for another chemical industry in South Africa. And of course, last but not least, hydrogen and the potential applications of hydrogen. If we get into those uncertain territories, in other words, where technology is still in its infancy, where there's still work to be done on the technology front, partial oxidation is maybe a slight version of the previous one, where people are looking at more optimized syngas platforms that will ultimately give you the access to, I think in particular, methanol for the downstream processing. But then when you look at start of the pathways for direct production, I guess there's a couple of emerging themes to watch. The first one would be oxidative coupling, which basically is a process where you can convert methane directly to the ethylene platform. And there's quite a bit of work both in the United States and China being done in this space. Second one would be pyrolysis and plasma, really trying to use high temperatures to achieve the same, give you a slightly different mix in terms of the product slate. And then I think the interesting thing is when you start to look at the biological pathways, when you start to look at methanotropic bacteria and the ability to basically genetically modify some of these bacteria to actually convert methane directly and produce some high desirable specific, because you modify them to produce specific chemical products. And I guess the last one would be syngas fermentation, which is maybe a slight version of the same. I think the problem there is lack of scale and I guess lack of specificity in terms of what you can produce, in particular when you start to chase the high-value molecules. So in conclusion, ladies and gentlemen, I think if we look at shale gas and the production of shale at commercial scale, I make the statement here to say it's been successfully demonstrated in North America. There's no need to reinvent the wheel. I think my message here is let's learn and adopt where necessary. Again, I think I've probably made it clear that if you look at an unconventional play such as the Karoo, it's not a short-term play. It will require time and it will require scale to be successful. I think environmental baseline monitoring is probably an absolute prerequisite here. If you look at all the noises elsewhere in the world, I think this is where they have actually fallen short. Without this, I think everything is open for debate or discussion. So if we look at the technologies required to develop a Karoo play specifically, I repeat the first thing, it's there. No need to reinvent the wheel, but my message would be think about how to support that in the long run when you do it locally. In terms of the downstream application, quite a number of applications. I guess the obvious choice would be why not petro-SA or gas to power. If you look at the development of a downstream industry, however, the cost of producing gas is going to be a critical parameter. And I think this might be a challenge in terms of the remoteness of the Karoo, the lack of infrastructure, and all the other challenges around that. So in conclusion, ladies and gentlemen, I think the Karoo, whilst it's probably it's attracting a lot of interest, still has a long way to go. With that, I thank you for your attention, and I would like to acknowledge one of my colleagues, John Cole. I started off by saying that I'm not necessarily an expert in the unconventional shale plays. John is sitting in the Canada office. He's actively doing that in British Columbia, so he's been hugely instrumental in providing the slides in the first part of the presentation. Thank you.